The last video for this chapter is going to be a really short one on survival curves. I didn't want to tack it on the end of the last one because I didn't want to have to rush through this. Um, Survival curves, we've sort of come across these before, but I just want to sort of talk about it in a bit more detail, and we'll certainly come back to this because these play such a huge role in terms of radiation biology. Um, but here are here's survival fractions on the y-axis. So at the top of the plot might be 1, right? So all the cells are surviving, and as you go down, the surviving fraction is reducing, but it's not reducing linearly, right? It's a logarithmic graph usually. So you go, 1 to 0.1 to 0.01 to 0.001. Like each increment as you go down on the graph would represent a factor of 10. So the effects are really quite pronounced. Usually more pronounced than it might appear. What's interesting here is that the late responding tissues and the tumor, or normal acute responding tissues, I guess, have different survival curves. In particular, the late responding tissues are sort of more curved, and the tumor and the early responding tissues are more straight. And that will play a really huge part in terms of how we can treat tumors with radiation while sparing normal tissue, especially if it's late responding tissue that might be in the vicinity of the tumor, and we really don't want to hurt that, right? We want to just hurt the tumor. So, coming back to this in a bit more data, it's being found that not only acutely and late responding normal tissues express the damage at different timescales, but that their survival curves are also different, right? So the curve for the late responding normal tissue is the curve you want, the one that sort of bends down more, and the acutely responding normal tissue is the one that is sort of more straight, right? The dark line in this, the dark black line in this case. And recall that these curves are usually represented by the linear quadratic model. Okay. So there's two different parameters in this model. There's the alpha, which is representing how straight it is, and there's the beta, which is representing the quadratic part, which is how bendy it is. And so if you divide the alpha by the beta, then you get a parameter which in effect is where if you were just to treat it as a linear response or as a quadratic response, it's where those two cross, and we'll come back to that later. But for now, that ratio is an indication of how straight it is. So for example, if the alpha is controlling how straight it is, and we look at alpha over beta, a bigger value will occur for straighter curves, whereas a smaller value will indicate more curvier curves, right? So we see that the alpha over beta can be around 10 grays for tumors. It does vary quite a lot. So this is just to sort of give you an idea. And the alpha over beta for late responding tissue, it's around 2 to 3 grays. So, which reflects just the fact that the late responding tissue is more curvier. And another way to think about this is, if it's more curvier, it's because there's more of a quadratic contribution. So this might be the fact that there's more radiation damage that is happening to one strand of a DNA and then happening to another strand of DNA, and both of those have to happen at the same time for the damage to occur, right? So that's happening more in those late responding tissues. Um, this will be really important, and we'll come back to the applications of this when we talk about dose fractionation, which is sort of included on the right, because in radiotherapy, you want to sort of make use of the differences between the tumor and the normal tissue. But we'll talk about this later on the course in week 11.